In this video, I'm going to walk you through the solutions for exam 2. Alright, so first of all, we had the multiple choice. Number 1, energy can be converted from one form to the other, but the total energy remains constant. That's the first law of thermodynamics. Okay, kinetic and potential energy are examples of macroscopic forms of energy. Microscopic forms of energy, that would be internal energy. And then here's the answer for the matching. You take the formula and match it up to the appropriate description. Okay, so I think that's straightforward. Here's examples of kinetic energy versus potential energy versus heat energy. So you can see the correct answers on this one. Voltage is joules per coulomb. Kvl, some of the voltage around any closed loop is 0. And it's truss members that are in compression that are most subject to buckling. Okay, so those are the multiple choice. All right, let's go through real quickly the workout problems for exam 2. So the first problem is to find the equivalent resistance, and so when I'm looking through here, I notice that these 3 resistors are in this same outer branch, so it's the same current flowing through them, so I know those must be in series. Okay, so I can add all those together and get an R1. All right, then I noticed that resulting R1, let me change the color here, R1 is in parallel with the 882 resistor. Okay, so I determine the parallel resistance, I get 630. So from there, you can envision it, but you would have this 630 connected to what's left. All right, and then what's left, the equivalent circuit's all in series, and so you add these together and you get the equivalent resistance being 1,000 ohms. Okay, in problem 10, I just simply wanted a free body diagram at the joint and for the members A, B, and BC in joint B. All right, so if I look at joint B, all right, one of the things that I do is I look at, first of all, BC was given to be in compression. Okay, so since BC is in compression, when I draw the free body diagram, this, let me change the color where you can see it. This is drawn into the joint, so that means it's in compression. All right, this drawing coming out of the joint means that I'm drawing that in tension. Okay, and so we know that AB is in tension. All right, and then of course there's this force acting down. Okay, so that's the free body diagram for the joint B. All right, and then what I wanted you to show me that you know is that you have the sum of forces on the joint. All right, so you do the free body diagram on the joint. And then the reaction at the members is in the opposite direction. Okay, so the joint BC exerts an external force on the member in this direction. Okay, so that would show that in compression. And then AB is in tension, so the opposite direction is pulling. All right, we know when things are in tension, they're being pulled. All right, so that's what I was looking for here. I got some crazy answers on the original exam because it became clear to me that not everybody understood exactly what I was asking for. All right, next, here's the power problem. I like these kind of problems because it tests lots of fundamental theories of electric circuits. All right, so first of all, you need to know Kvl and Kcl. All right, so we're looking for example, VE. All right, let's say we wanted to know VE. All right, I can go in a loop. All right, and I can go in any loop. All right, so I would want to go through a loop where the only thing unknown is VE. So if I went this direction, then what I would see is I have, coming this way, I have a drop of 10. Okay, and then I also have a drop of 30. And then coming on around, I have a rise of VE. All right, so VE is 40 volts. Okay, so I would put that into my table. All right, and the next thing I would do is I would look at the currents. Okay, so in this problem, you were given that the current you were given this 1 amp current, and you were also given this 4 amp current. Okay, so I can take a look at this node. I have this coming in, this coming out, and then I would have the current going through C coming, I referenced it to come up this way. Okay, so IC is going to be, you write KCl equation. So the sum of currents coming into the node equals the sum of currents going out. All right, so coming in I have 4. Coming out I have 1 plus IC. All right, so I can solve for IC, and I would get that that'd be 3 amps. Okay, so that goes here. All right, the rest of these were given in the problem. Okay, and so you calculate, well, no, I needed VA. And so you write a KVL equation, you get VA to be 5 volts. Okay, so from here, it's just a matter of looking at the sign convention to tell whether this is using power or supplying power. So let's take a look at A. Okay, so VA is 5 volts, all right? And then the current is coming this way, right? I extend this 1 amp around. It's coming this way. That's in the direction of a drop, all right? Because it's a drop, the power is the product of these two, so 5 times 1 is 5, and this would be 5 watts used because it's the passive sign convention. If current moves in the direction of a drop, it's passive sign convention. So a positive number there would mean it's using power. Okay, so for B, this was given, but we can check it. This 1 amp is moving in the direction of a rise. All right, so 35 times 1, that's the positive number, right? 35 watts. And because this is the active sign convention, it would show up on the supply side of this chart. Okay, so we go through the rest of these. For BC, I have the current moving up, all right? And so that's in the direction of a rise, so 30 times 3 is a positive number, it's 90 watts, and that would be supplied. Okay, so walking you through that, you fill out the tables, and then at the end, what I want you to do is check to see that when you sum the columns, all right, so I get 165 on the used side, and you sum the supply side, you get 165. These should check out according to the conservation of energy and power. Okay, so that's that problem. Okay, I also wanted to give you an easy circuit problem on this exam. And so the idea here is hopefully to go to easy equivalent circuits. So I wanted to know IA, and so what I was hoping you would see is to easily convert this to a different, easier circuit. So if I combine these in parallel, 6K in parallel with 3K gives me a 2K. All right, and so I can have this as an equivalent circuit. The nice thing about that is, now that this is 2 milliamps times 2 kiloohms, you can calculate using Ohm's law, this should be 4 volts, right? 2 times 10 to the minus third times 2,000 gives me 4. Okay, so the significance of that is I know that these two resistors are in parallel, so this is also 4 volts. All right, so if I know the voltage across a resistor, I can calculate the current. So in this case, IA is the 4 volts divided by the 3K ohm resistor. So you get 1.33 milliamps. Okay, so that's that problem. Okay, for number 18, it's the same type of deal. I wanted you to see that you come up with an equivalent circuit. So the first thing I noticed is 18 in parallel with 36. That gives me this circuit. Okay. From there, I can collapse this down to a single loop circuit and apply Ohm's law. It's real easy to see this is 1 amp. Okay, so the current supplied by the 30-volt source is 1 amp. All right, so next I need to know the power associated with the 36 ohm resistor. So I'm thinking, wow, if I had this voltage across the 36 ohm resistor, I would be able to easily calculate the power. Okay, and so if I go over to this equivalent circuit, I can tell, because this is 1 amp and this is 12 ohms, 1 times 12, this should be 12 volts across here. Okay, so you can calculate the current through it and do I squared times R. So 12 over 36 is the current through the 36 ohm resistor. I squared times R gives me the 4 watt answer. Okay, now let's get to the truss problem. Okay, so for this truss problem, you were supposed to find the member forces CD and CB. And there's a hint, you don't have to analyze the whole truss. All right, so if you were going to just do these and you were given some given some values for other members, you could write the equations and save yourself some work by just looking at the correct joint. All right, so we're thinking here that I want to find CD and I want to find, CB and I want to find CD. All right, this one is known. Okay, so we don't know these, but we do know this one. Okay, and so that means at this joint I have two unknowns at a single joint. If I have two unknowns at a single joint, I can solve for the unknowns, right? Because the sum of forces in the x direction gives me one equation, sum of forces in the y direction gives me the other. Okay, so I draw a free body diagram of joint C, and the way I did this is I knew that AC is 184.3 pounds in compression, so I drew this coming into the joint. I drew it in compression. Okay, I can calculate this angle alpha, by the way, because I know this is 2.5 and I know this rise is 3.5, so alpha is just the arctan of 3.5 over 2.5. All right, I can also get this angle beta. All right, so I drew these other two forces, CB. This is unknown. I draw it in tension just because that's the standard practice. So I draw both those in, I draw those in tension, and I can calculate beta. Beta is the arctan of 3.5 over 7.5. All right, so that's looking good. Now I'm thinking, wow, this is just solving a system of equations that are written from sum of forces in the x direction equals 0, sum of forces in the y direction equals 0. Okay, so if I take the sum of forces in the x direction equation, I can see that I have the 184.3 times cosine alpha. All right, project that down, I get the cosine. All right, plus I get CB, right? This is moving in the plus direction, plus is to the right. CB times the cosine of beta, and those are the only two things in the x direction. Let that equal to 0. All right, so I know alpha, I know beta, I can solve for CB. All right, I get a negative number here. I had drawn this in tension. What that means is that CB is actually in compression. All right, so and finally, to solve for CD, I can write sum of forces in the y direction equals 0. All right, so in the y direction, I have 184.3 sine of alpha moving up, Then I have CD moving down. CD's completely in the y direction. And then moving down also I have CB sine of beta. And I forgot on my free body diagram that there's a 200-pound force that's acting at the top here. That's the load. Okay, so that goes down. All right, so I have this equation for CD, and it turns out if you carried all the precision through, that's a zero force member. So the answer here is 0. All right, so that's how you solve that one. That's a hint for other exams. This would be a substantial problem to solve if you were asked to solve for all the things that are unknown. All right, so if I just gave you this and asked you for reaction forces at A and B and all the member forces, it would take you a while to crank through that. All right, so that's a very common thing that I'll do for exams, is I'll give you part of the answer and ask you to complete the rest. All right, so hopefully that'll help with that. Okay, and the last one for the walkthrough on problem C. There's a little bit of confusion on this, and I made the toy really, really light on purpose just because I didn't want you to have to worry about the initial value of the spring compression. Okay, so essentially what we're saying is this toy is so light that it doesn't really compress the spring. All right, so at rest we have 10 centimeters, and we're going to add work. All right, so I have this in orange. Add work here. This is external to the system to compress the spring. All right, so once we have that compressed, this is our system. All right. Okay, so this is one time of our system, and then we're going to have a final time of the system with this scenario. Okay, so I call that Ti and Tf. All right, so what we know is that the potential energy for time 1, or time I, plus the kinetic energy at time I should equal the potential energy at time Tf plus the kinetic energy at time Tf, because there's no other work being added to the system. Okay? All right, so everything else in the energy balance equation cancels out. There's no heat transfer. There's no external work being done. It's just pure release of potential energy and to convert that to another form. The other thing that we have going for us is that we know at the initial time the velocity is 0. So that means the kinetic energy is 0. Same thing with the final time. This has reached its peak value, so the little army man goes up to the top and then reaches 0 velocity. And that's when we stop and take a look at how high that is. And so the kinetic energy at that point is also 0. So it's just a pure trade of potential energy. In system 1, though, we have two kinds of energy. We have potential energy. We have potential energy due to gravity, and we have potential energy stored by the spring. Okay, so I said in the problem statement that the reference should be the table. All right, and so calculating the potential energy due to gravity is just mgh1, where h1 is the 6 centimeter height of the spring. And then we have the potential energy stored in the spring, which is 1/2 k x squared. Now I called it x because what we're doing here, let me change the color again, we're going from one value, which is the spring at rest, that's the 0 point, and we're compressing it down by 4 centimeters, or we're compressing it down by x. Okay, so the formula for potential energy would be 1/2 k x squared minus 0 squared. All right, so that's what I have here, where x is equal to the 4 centimeters. All right, it's not the 6, right? Because we go from 10 down to 6, so the total difference is 4. All right, so that's the main setup. I set these two, potential energies equal to 0, and I'll have on one side of the equation H max, and then the other side of the equation is over here, so I can rearrange to get this form of the equation. and then it's just a matter of plugging all the values into the calculator, and what I get is 75.3 centimeters as the answer. Okay, so that's a quick walkthrough of exam 2. Hopefully that helps, and hopefully you can work similar problems for the final.